This is the OpenHBI course Linked Data Engineering, Lecture 1, Linked Data and the Web of Data. In this third part of the first lecture, we will talk about a universal data representation or knowledge representation which is used for the Web of Data and for linked data. The data representation we are going to look at is the so-called Resource Description Framework, RDF. And facts, knowledge or data is expressed with the help of exactly this framework. Okay, but first let's have a look at a simple example of knowledge representation and ask ourselves the question, how should we represent the following fact that Pluto has been discovered in 1930? Some of you who do data engineering, for example, or data design, they might say, okay, let's define a UML instance. There we have an instance which is Pluto. Pluto is a planet and it has been discovered in 1930. Of course, you can do that. Another way would also be, let's try to code this information in HTML. So we have Pluto and then we write there as a text has been discovered in 1930. And to make a little add-on, we can, for example, link the word Pluto to its representation or its Wikipedia page. So to its representation in Wikipedia. This could be an HTML representation, meaning exactly the same. What else? Try it in XML, which is the extensible markup language. There you have several possibilities to express the fact. One of them is here. You define planet and you give it two properties. You say first you have an attribute name, which has the value Pluto, and you have an attribute discovered, which has the value 1930. And you mean by that that Pluto has been discovered in 1930 and Pluto is a planet. Quite nice. But even in XML you have several possibilities to express exactly this same fact. So, for example, you could make it much more explicit. Here you define something which has been discovered and you say the discovery is Pluto and the year is 1930. Or you say you have a planet which names as Pluto and then you have a property that you call year discovered and this then has the value 1930. Or the same representation that we had before, the shorter one, planet with two attributes, Pluto, and discovered in 1930. The problem here is there a unique representation or something which is something intuitively known to the user? So how could we intuitively model exactly this knowledge? With XML it's really difficult because you have several ways to express this, but you have no way to express the meaning behind that. So this is somehow lacking. So you need another kind of knowledge representation for that, and it should be much more concise and possibly as unique as possible. With XML, of course, you have the possibility to transform one XML schema to another XML schema. You do this via so-called XML style sheet transitions or transformations, so XSLT transformations. This is, of course, quite expensive because for every schema you need a new transformation. And of course, if you want to translate between several schemata, this or the number of transformation grows then in the end in a quadratic way. So this is, of course, no way to do that. What you need is somehow like a unique representation, but this can be based usually only on XML. You need something more restricted like that. So, the question again, how do I represent the following fact in a most intuitive way? So this is a fact. So simply let's analyze what is in this fact. So we are talking about something which is Pluto. So this is the subject we are talking about. Okay, this is the first thing. Then we say, this subject has a specific attribute, property, or predicate. So the sentence, sentence, subject, predicate, object. So here we have the predicate has been discovered in. So this is something like a property or an attribute which could be mapped to the subject Pluto. Now the question is, we need a value. So when has it been discovered? In 1930. This would be the object of our sentence. So you see here clearly this is a basic fact which can be separated in subject, predicate, object, which means we have a threefold proposition which says that a specific subject has a specific predicate and this predicate has a specific value. And this value is here the object. So this is an interesting analysis. And if you put this in a graphical representation, you could end up in something like a directed graph. Simply represent subjects and objects as kind of vertices or nodes, and the predicates then are the relations between the nodes. They are the mappings from one entity to another entity, from one entity to a class, and they somehow express the meaning or signify the meaning of their relationship, which then is kind of a predicate or property value. So this could be a quite intuitive knowledge representation for directed graphs. But graphical way, it's not necessarily the most handy way to deal with large knowledge representation. So we must find somehow also a kind of sequentialization or serialization of this kind of knowledge representation. And this can be achieved with a resource description framework. What is the resource description framework? Usually it's part of the so-called semantic web stack. So there it's in a specific layer, and this is used for knowledge representation. So let's have a look at RDF. First, resource. What is a resource? So everything can be a resource, and you can make assumptions about nearly everything. A resource is something which can be uniquely identified and which can be referenced with the help of a URI on the web. So it means you must have a web address, and then, of course, you can make assumptions about this thing on the web. We are dealing with the web, therefore everything can also be represented in the web. Also things in the real world can have a URI. We will come back to that later on. But of course, to talk about that on the web, we need a web-based identifier, and this is the Uniform Resource Identifier. Then you give descriptions, so you describe the resources, and you do this usually via representing properties and relationships among resources as graphs, as we've seen it before. And of course, all this is then put together in some kind of framework of web-based protocols. So you use the URI for identification, you use HTTP for transporting messages and information, you can use XML, Turtle, JSON, or any other kind of serialization which is available for RDF. We will look into that deeper on. And of course, to make sense of it, everything must be based on a formal model, and this is the semantics behind the framework. So knowledge in RDF is expressed as a list of statements, and all of these statements follow the same simple schema, the so-called RDF triples. As we have seen in the graph, this is threefold. We have a subject, we have a predicate, we have an object, and this forms in the end an RDF triple. So we have Pluto has been discovered in 1930. You see here, this is Pluto. We need a URI for that. This here is the predicate or property. We also need a URI to identify that one. And then, of course, we have the object, which can be either another entity, then we need a URI, or it can be simply a value, which then is expressed as a literal. A literal can be, for example, a character string, it can be any kind of number, or it can also be something like a typed literal. You can say this is a number, and the number is expressed, let's say, in floating point notation with double precision or something like that. So this is also possible with the resource description framework. So you have this threefold splitting. You have RDF triples. Subject is a URI. Predicate or property is a URI, and then the object can be a URI or a literal. So this is usually the rule: URI, URI, and then URI or literal. These are the RDF building blocks. You see here again the graph representation, here again with URIs, which denote the subject, the property or predicate, and then the object. And of course, I can also write this down in a serialization. This is the most simple serialization for RDF. It's called N-triple serialization. And then you have here the subject, Pluto. And then you have discovered, also taken from the URI, from an ontology where you have discovered. And then you have a literal 1930. A literal character string is usually expressed, as you see here, in these double quotes. The interesting thing is now, where does this URI come from that I use here? So usually this URI is on the web. It means this must be dereferenceable. So I must be able to click on it. So let's try to click on it. I have, of course, put a link behind that. And then we will see, now we have to do it again here. We will end up at DBpedia. Probably you have never heard about DBpedia, but this is the semantic web version or linked data version of the Wikipedia. We will come back to that later, how Wikipedia is transferred into this RDF representation. And this is, of course, an RDF representation of the knowledge which is somehow part of Wikipedia. And of course, if you dereference this URI, you will get information from DBpedia, which stems from Wikipedia, about planet Pluto. So for example, you will see things like, for example, there is an abstract which describes somehow this entity, and you will see lots of data which is available about Pluto, like, for example, the mean temperature, for example, or other things like the albedo, alignment, angular size, and stuff like that. So I'm not an astronomer, so therefore many of this data does not make sense for me, but I can access the data, and probably I can also make sense of it. So let's go back to our graph representation. So starting with the first RDF triple we have looked at, we have here Pluto has been discovered in 1930. The interesting thing is, of course, you can follow this knowledge, and there is lots of interesting facts. For example, also the discoverer of Pluto is referenced here, and this is Clyde Tombaugh, and he's also part of DBpedia. And then if you click on Clyde Tombaugh, you might get interesting information like, for example, his birth date or his birthplace, which is Streator in Illinois. And then, of course, you click on Streator, Illinois, and then you will end up with another interesting fact, for example, that the motto of this interesting city is Quiet Surprise in the Prairie. So we can have a look at that directly in DBpedia. So here we have Pluto. Now let's scroll down and see if we find Clyde Tombaugh, who is the, here it is, the discoverer. You see here, DBO discoverer, Clyde Tombaugh. I can click on Clyde Tombaugh, then I'm at Clyde Tombaugh. I get information about this guy here again. So, and one of the information I get here is the birth date, and the birth date here you see is the 4th of February 1906. And of course I must get his birthplace. Do I get it, birthplace? Yeah, here we have Streator, Illinois. I can click on it, Streator, Illinois, and I go down. I will find the motto, I guess. Yeah, here you have the DBO motto, Quiet Surprise on the Prairie. So this is a network of data. So this is a huge database, and the data, as you see here, is interconnected, and the data itself, the entities, are identified via URIs. And you see here the access. To access this URI on the web, you use the HTTP protocol, and there is a representation which is also available for your browser. So also humans can consume this data from the web of data. Of course, also machines can do this, but how do machines then interpret this data? We will see later. Okay, so let's get back to our presentation. This is the graph representation, and now let's have a look at n-triple representation of exactly the same knowledge. I have here colored all the subjects in blue, the properties in red, and the objects in green. So these are a bunch of RDF triples. Let's have a closer look on that. RDF usually is a triple model. So we have subject, predicate, object. Every piece of knowledge is broken down into that. On the same hand, RDF is also a graph model, which means every piece of information can be interpreted as a vertex, an edge, and another vertex. So we have graphs and we have this triple model, which are somehow exchangeable. It's only a way of interpreting this knowledge. We have just seen this on the example. Usually then, in our RDF triples, we are talking about entities. And these entities, about these I try to formulate or represent facts which represent some knowledge about these entities. And the entities here can be, of course, either part of the subject, or they can be here part of the object. Then I can also have classes here. So for example, I can say that Pluto is a celestial body, and then of course I need in the object some class representation, and also the URI of a class, which is here celestial body, or it's also a place. And what you see here, for example, you have different URIs. So the celestial body we take from DBpedia, or the place we take from schema.org, which is another interesting vocabulary issued by the major search engine companies, for example Google. and which can be used to express knowledge. So this is a class with places, so with geographical locations. Interesting thing. Then, of course, an object can also be represented as a literal. In RDF, literals usually are written here in double quotes. So here, for example, you have 1930, or you have a representation for a date. But you can also give this a type. So then you interpret this character string as a typed information. So for example, here you have a geographical latitude and a geographical longitude for Streator, Illinois. And this is given as a number with as a floating point number. So this is an example for a typed literal. What else do we have? We have these properties. Properties are always expressed as URIs. And if you try to reference or to dereference these URIs on the web in the web browser, you will get some information behind it, some information in human-readable form as well as information in machine-readable form. We will get back to that later on. But this is the benefit of referencing everything with the help of a URI, because then you have a network, a web of data. And the nice thing is we do not have to invent all these vocabularies by our own or these URIs of our own, because simply there exists quite a lot on the web. So we have, for example, all the knowledge which is represented in Wikipedia, and we have this in DBpedia. So DBpedia stands as a reference for many objects in the real world, for example. And there are also ontologies and vocabularies defined for the most common properties, which are also represented in DBpedia. So therefore, you will rather often see URIs stemming from DBpedia. And there are other, as you see here, namespaces used. Schema.org is used here, or we have here the W3 namespace, once for the RDF vocabulary or for the geo vocabulary, where different kind of properties are defined and can be referenced. So these are the building blocks of the resource description framework, which we deal later on in more detail. What we will do next is we will have a deeper look, or a first course look, let's say, put it that way, on the semantic web technology which is behind linked data. And we will have, in part 4 of the lecture, a short tour through the entire stack of the semantic web layer cake.